You're listening to Radio Galaksija, Radio Galaxy, science radio show or podcast, whatever you like more, from Belgrade, Serbia. My name is Dusan Pavlovic, and yes, this episode is in English for change, and with a good reason. During the LHCP conference, or Large Hadron Collider Physics conference, which was held in Belgrade a few weeks ago, we had an opportunity to talk to Professor John Ellis, one of the most prominent particle physicists who is active in the field of theoretical and experimental particle physics at CERN and other prominent research institutions for more than 50 years, half a century. Professor Ellis is a British theoretical physicist, born in 1948 and currently holding the Clerk Maxwell Professorship at the King's College of London, which is the professorship held by James Clerk Maxwell himself in the 19th century. His activities in CERN are wide-ranging, and currently he is a chair of the Committee to Investigate Physics Opportunities in Future Proton Accelerators, and also a member of the extended CLIC, or Compact Linear Collider Steering Committee. His career goes way back to the beginning of the standard model of elementary particles, and even now he is one of the figures which are dealing with all kinds of different topics which are going far beyond the standard model. After 2012, when the Higgs boson, was experimentally confirmed, a lot of new issues and problems occurred, including the detection of dark matter particles, gravitational waves, etc. John is one of the people who work extensively on new solutions, experimental as well as theoretical, to deal with the problems beyond the ruling paradigm or normal science in Kuhnian sense in particle physics, and he is trying to tackle and figure out the direction in which particle physics should go in the near but also far future, in the next decade, but also in the next few or even several decades. I had a conversation with him about the future of particle physics, crisis in particle physics in a Kuhnian sense, about some new experiments which are ongoing or will be built in the next near future at CERN, and also in United Kingdom. We talked about the dark matter and the connection between particle physics and cosmology, as well as astroparticle physics problems, about the unification of theories and the theory of everything, a term which, by the way, John himself coined, and several more topics from John's rich experience and work. An hour-long conversation, a lot of questions, and a lot of interesting and important insights from Professor Ellis's experience and knowledge, and I hope that it will be inspiring for all of you who are interested in mysteries of contemporary particle physics and all kind of open questions about the theory and experiments which are frontier science in physics today, and not only in physics. And before I let you listen to the conversation, I want to emphasize how grateful I am to Professor Ellis for dedicating a whole hour to Radio Galaksija, as well as to the organizers of the conference, especially to Slobodan Bubnjevic, who was responsible for this opportunity, for this meeting to happen. So, without further ado, enjoy the listening and enjoy the further digging about the topics and problems we talked about in the next hour. Thank you, John, for coming. It's a really big pleasure to have you here, and you're the first who I interviewed for the Radio Galaksija radio show, podcast show in English. So let's start with the field you're working on for years, for decades, in CERN, in King's College London, even before you even thought about going into that field when you were young, because I think it's a really nice and interesting perspective to give to the young people who are who like to come and start working in theoretical physics, theoretical particle physics. But I think the atmosphere is much different today than it was when you were starting, because a lot of things happened, and in a way the particle physics is in some kind of crisis today, or not, maybe. I don't know. So maybe we can start with the question and about the what is particle physics now, and in a Kuhnian sense, what is the normal science which particle physicist is working on now at CERN, not only at CERN, and what are the issues with the normal science from which maybe it is destined to arise some new physics or new paradigm. And what do you look at that? How do you look at that?
Well, if you agree, I think I can start back when I was 12 years old.
Okay.
So that was when I first started getting interested in particle physics. I used to borrow books from the local public library, mainly non-fiction books, because the kids' stories I found very boring. And so I would take out books on mathematics, physics, and the universe, astrophysics and cosmology. And I guess that was when I got interested in particle physics, which of course is the study of the fundamental constituents of matter. And I also got interested in the connection between those fundamental particles and the structure of the universe, cosmology, the universe on the largest possible scale. And of course, in order to make a connection between the two, you need mathematics. So that was the sort of the set of topics that I got interested in. Then moving on a few years, when I started doing research, the professor asked me, well, what sort of research in theoretical physics do you want to do? And I said that I wanted to do work that was closely related to experiment. So I'm not a sort of pure mathematical physicist. I'm somebody who likes to try to understand what the data are saying and to make predictions that can maybe be checked by experiments. So that's very much my driving influence, I would say. So anyway, so where are we now with particle physics? So back in the 1960s, a theory was proposed that we now call the Standard Model, which works incredibly well. The first experimental verifications of predictions of the Standard Model came in the 1970s. In the 1980s and 1990s, very detailed high-precision measurements were made, which agreed with the Standard Model. And in the 2000s, we were in a situation where everything seemed to be working fine, but there was one particle that was missing, the famous or infamous Higgs boson. And this got quite a sort of mysterious aura to it, because it's a very different type of particle from all the others.
In what way?
Well, the fundamental constituents of matter, the electron, the quarks that make up nuclei, those all have spin, half a unit of spin. And the forces between them are mediated by particles, which again are spinning, but with one unit of spin. The classic example being the photon, but the same is true for the other fundamental interactions. And we understand pretty well how those particles of spin 1/2, of spin 1 work. But the Higgs boson would have to be a particle with no spin. And because it has no spin, its properties are relatively unconstrained. So just as an example, it can couple to matter particles with very different strengths. Mm-hmm. And in fact, one of the big puzzles is that we don't understand the values of the interactions of the Higgs boson with the particles of matter. We don't understand that they vary over 5 orders of magnitude, and we just don't have a theory for all those different types of masses and different strengths of interaction of the Higgs boson.
So the Higgs boson, as such, is the prediction from the theoretical structure of the Standard Model, and its detection was missing.
Right.
But not also that was the problem. The problem was also to understand all kind of different interactions with the particles within the framework of the Standard Model, or that was something which a Standard Model does not deal with.
So there are various things that the Standard Model does not deal with. So it doesn't tell you, for example, why the muon weighs 200 times more than the electron. It just does, and you can describe that in the Standard Model, but you don't have a fundamental understanding of it. And also, you don't understand the mass of the Higgs boson itself. So when the theory was originally written down, it was a completely arbitrary parameter. And then people thought, well, this is supposed to be a consistent quantum theory, let's calculate quantum effects. And they found that they were infinite, very infinite. So that then raised a big problem. Why should the Higgs boson have a mass of a few hundred times the proton mass, which it had to have for consistency of the theory? And that's an issue which we still don't understand. And we have various theories for why that might be the case. Many of those theories predicted additional phenomena, like, for example, supersymmetry, which in principle could relate matter particles to force particles. Or maybe there might be additional dimensions of space, which is one of the possibilities that Einstein considered in his later years, and an idea that's become very fashionable in the context of string theory. But so far, although our experiments have verified the existence of the Higgs boson, and it seems to do what it should do according to the tin, we haven't found any of these other phenomena that we were rather expecting to discover. So when the Large Hadron Collider at CERN switched on at high energies in 2010, people thought, well, maybe we're going to discover gazillions of new particles beyond the Standard Model, and then eventually maybe later on the Higgs boson. In fact, we discovered the Higgs boson surprisingly quickly, and we haven't seen those gazillions of other particles. And this is a problem, because it really means that we don't understand the Higgs boson. So if I go back again to when I was a student, these ideas that I've been discussing had been proposed, but people weren't really paying attention to them. And particle physics was in some sense in a state of crisis. People were making additional detailed measurements, but the grand vision was lacking. And then in the 1970s, predictions of the Standard Model started getting verified, and so we knew what direction we should be heading. So we entered a different phase of scientific development. So in some sense, we've now completed that piece of the journey. We got the Standard Model, and it works. We don't really understand why it works, but it does work. That again leaves us in a situation of confusion. We don't know where to go next. Well, we can see lots of puzzles, and we've got all sorts of ideas for how those puzzles might be resolved, but so far there's no experimental evidence for any of them. So in some respects, I would say that the situation in particle physics now is sort of more similar to what it was when I started as a student,
Then in 70s.
And in the intervening period, there was a sort of current pointing flowing in a particular direction. But now we seem to be in a whirlpool where we're going around and looking in all sorts of different directions and not finding anything.
I suppose that goes with the problem of Higgs particle mass, which was expected to be much higher, if I recall, or lower, but it was calculated from the detection that it is much lower than we think, and there are no extra particles which were made in the collision, which could compensate that missing mass, let's say, if I understood well. Yeah, that's one of the problems.
Yeah, so I would say for about 40 years you could get kind of an argument as to whether the Higgs boson actually really existed, or whether what was called the Higgs boson was really just a placeholder for some sort of unknown physics. And, well, it transpired that actually what was written down originally by Peter Higgs in 1964 and by Stephen Weinberg in 1967, the particle that has been discovered at the LHC seems to behave in just exactly the way that it did in their original theory, which was regarded by many people ridiculous. It's too naive. It can't possibly be like that. But so far it is.
It is, yeah. And also, when you are saying that the particle physics is in let's say, in a way, back to where it started as not as that we don't know things, but there are all kinds of different directions where that can go. What are those directions from your experience point of view and from the particle physics community? And
yeah, well, I should say that perhaps we put the Higgs boson in a more general context. So there are various different fundamental interactions amongst the constituents of matter. There's electromagnetism. There's the strong interactions that keeps nuclei held together. There's the weak interactions that generate forms of radioactivity. And it all looks very complicated. And so a lot of people, myself included, in the 1970s said, well, maybe we should try to make a more unified theory where you put all those interactions together. And some very interesting ideas along those lines have been proposed. And there's maybe a couple of pieces of indirect evidence that those ideas might have some truth to them, but there's no direct evidence. And so one of the direct pieces of evidence that was looked for was in these theories, protons can decay with a very, very, very long lifetime. So it's like a form of radioactivity, but much, 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 much weaker than the form of radioactivity that we know. That was the theoretical suggestion. But that hasn't been seen. And I personally haven't given up on that. And in fact, I'm a member of an experimental collaboration which is building a big new detector which maybe could look again for decay of the proton.
And what are the problems for detection of the proton decay?
Well, first of all, if the proton does decay, the lifetime is incredibly long. We're talking about 10 to the 34 years.
Okay.
So there's no good just looking at an individual proton and waiting. That's not going to work. What you have to do is get a very big amount of matter together, and 500,000 tons, and then you have to shield it from all sorts of particles coming in from the outside. In particular, cosmic rays produce a background. Cosmic rays include neutrinos, and if they hit a nucleus sitting inside your detector, it might look like proton decay. So, so you have to combat that background. Anyway, so I don't know whether this new experiment will find proton decay, but that's one of the directions that we're looking in.
Is it possible today to build a chamber which is, ideally isolated from all kind of influences from the surroundings? Oh, okay.
Well, you can't shield yourself from neutrinos. You can shield yourself from everything else.
Mm-hmm.
And to do that, typically you go underground, a couple of kilometers underground. And if you have a very big detector, then if there's stuff happening in the rock which sends particles into your detector, typically they don't get very far. They just get sort of stopped on the outside of the detector. And so you can remove those and just look at the inside of the detector.
Mm-hmm.
So we'll see what happens.
Mm-hmm.
So anyway, so there's this idea of unifying the fundamental forces, and it hasn't produced any direct evidence so far, but maybe in a few years' time. Then I was talking about the connection between particle physics and cosmology. So one of the biggest puzzles in cosmology is dark matter.
Mm-hmm.
So astrophysicists tell us that in order to hold galaxies together, in fact, in order to form galaxies in the first place, we need, in addition to the visible matter, some sort of invisible, weakly attracting dark matter.
Mm-hmm.
And there have been various ideas what that might be. So there's this theory that I've been a fan of for a long time called supersymmetry, and that theory naturally predicted a candidate dark matter particle.
Mm-hmm.
Also, some theories with extra dimensions of space also predicted a candidate for dark matter. But those particles haven't shown up yet, which doesn't mean to say that they don't exist, and there are ongoing experiments to look in more detail. Again, we come back to large detectors deep underground. But at the moment, I think we're kind of not sure whether that's the right direction to go for dark matter or not.
And what are the characteristics of those particles which supersymmetry goes on for the dark matter?
Okay, so the theory of supersymmetry says that for every matter-like particle, which has half a unit of spin, there should be some matter-unlike particle
mm-hmm.
with either no spin or 1 unit of spin, which would have identical internal properties, but spins at a different rate. Mm-hmm. And the lightest of those new supersymmetric particles would in general be stable, mm-hmm. and it's quite likely to be a neutral particle with very weak interactions, mm-hmm. in which case it would be a great candidate for the dark matter. And the theory predicts that it would weigh maybe somewhere between 100 and 1,000 times the mass of a proton, the mass of a hydrogen.
It's a massive particle.
Yeah. So in recent years, people have been exploring alternative possibilities because those searches are not successful. I should mention also that experiments at the LHC have also been looking for that type of dark matter and not found it. Mm-hmm. So people are now thinking about looking elsewhere, under a different lamppost, if
mm-hmm.
you like.
Mm-hmm.
And so one possibility is that the dark matter doesn't consist of individual particles, but actually the dark matter is due to coherent waves or clouds of particles that cling together in a sort of quantum mechanical way.
Mm-hmm.
And so that's a theory which is attracting increased attention at the moment. And in fact, another one of my experimental interests is an experiment to look for that type of dark matter candidate using the quantum properties of atoms.
Mm-hmm.
So according to quantum mechanics, you can have things in two states, but they can interfere. Mm-hmm. And that's in particular true for atoms, and that's been observed in the laboratory. And that sort of atom interference could in principle be modified if there's this cloud of dark matter. So that's an effect that we're preparing an experiment to look for.
So if we have two atoms of matter, which in their superposition are giving the quantum, I don't know how to say that, quantum signature of that interacting atoms, we can modify that, or that can be modified with the appearance of the dark matter.
Right, so if the dark matter interacts with the atoms, and what you do is you sort of separate out the atoms into two clouds, and then you bring them back together again and look at their pattern of interference. And the ultralight dark matter particle that I was talking about, the cloud, the wave, could have a different height over here than what it does over there. And so when you bring them back together, that's going to affect the pattern of interference. So, as I said, I'm involved in an experiment which we're preparing to look for that. Actually, my main interest in that sort of experiment is not so much to look for dark matter, of course that's very interesting and important, but to look for gravitational waves. So in the same way, if you separate your cloud of atoms into two pieces and you bring them back together again, then maybe the gravitational wave affects one differently from the other, and that is a very promising technique for looking for gravitational waves which is different from the way in which they've been discovered up to now.
And at what level of precision are those measurements made of, and what should be the setup, experimental setup for that? And what is that the experiment you're working on, and is it at CERN or?
So the prototype for this experiment would be in Oxford, in England. So the idea is basically that you have a source of atoms and you throw them up, and you watch the way they go up and then they come back down again, and you bombard them with lasers in such a way that some of the atoms go further than others, and so they get separated, and then if a gravitational wave comes by or some dark matter field comes by, then it could affect those two sets of atoms in different ways, and you could detect that by doing this interference.
But you also have an interference from all kind of other things which happen on Earth and so on and so on. And, how do you exclude those?
Indeed, that is an issue, and you don't have to worry about cosmic rays or radioactive particles. That's not the problem. The problem is that the Earth is shaking all the time. So, for example, this prototype experiment that we want to build in the Oxford Physics Department, there's an elevator, goes up and down.
Okay.
There's people walking around. There's rats in the basement. And as they move around, they generate a gravitational field, and this detector is so sensitive that it's sensitive to rats. Right.
Yeah, it's similar like LIGO experiment.
Right. So I have a group of people at King's College London who are looking into this, and so we think that we can combat this gravitational noise, at least at some level. But this is something which we need to study in more detail. Maybe the answer is that around the detector you put lots of very sensitive seismometers, and the seismometers measure the vibrations of the Earth, and then you can subtract that out from your detector signal.
So,
and maybe we have to use rat poison.
So yeah, one side is to exclude everything you can by physically removing it, and the other is to record that, and then just on the level of data measurement and so on to subtract that.
So one of our students has been devising filters that can, for example, get rid of the elevator going up and down. And he thinks he can also get rid of the rats, but still working on it.
Yeah, and that idea is how old? Is it something which is, I don't know, last 10 years, your idea, or there was an idea before and now is the time to try to make that because the technology advanced so much that it is now?
So the idea that you should be able to observe atoms interfering, this is an old idea, probably goes back 30 years. And people have been building devices for maybe 20 years to actually do real experiments with it and look for new physics. And in particular, there's a group at Stanford University that's really been working very hard on that, led by a guy called Mark Kasevich. And so we are sort of, if you like, following in their footsteps, but using, I don't want to get too technical, but using a different element from what they've been working with up until now, because this element has, we can give a bigger kick to the atoms. We can separate them more, and by separating them more, then we get a greater sensitivity to these possible waves of dark matter or gravitational waves. So we'll see.
Okay, nice story. Could you tell us, is there a name for that project for people who can maybe search and look into details?
Yeah, so the project's name is AION, A-I-O-N.
Okay.
So Atom Interferometer Observatory and Network.
Okay.
So I think if people Google AION, they're probably going to find some, clothing company in Bangladesh or something, but they should also find our experiment.
Yeah, so it can be related to the artificial intelligence, something like that. Yeah. Okay, so that's an Oxford project you are working on. But you also work on some projects for detecting new things in particle physics in CERN. I saw that there's this new muon collider idea. There's also this CLIC accelerator and so on. So new accelerators at CERN. Can you tell us more about that?
Yeah, so there's various different ideas for the next generation of particle colliders. So I gave a talk here in Belgrade yesterday, from little bangs to the big bang. So there's lots of ways of making little bangs. And one possibility is to collide protons, which is what we do at the LHC. Another possibility is to collide electrons and their antiparticles, positrons. And another way is to collide muons with antimuons. Now, nobody's done that, and it requires a lot of technology development.
So this third type, so electron-positron is a large LEP, yeah. So
basically, we think we have the technology in hand to collide electrons and positrons.
Okay.
Indeed, back in the 1990s, we had a large electron-positron collider, Large Electron Positron LEP, which really put us on the right track as far as the standard model is concerned. And so one possibility is just to do the same thing but bigger and make much more precise measurements. So that might give us some indirect indication of what physics there is beyond the standard model. And if we were to do that, then we would dig a big new tunnel, and then as a later stage we could put in protons. And so just as the Large Hadron Collider has followed on from the Large Electron Positron Collider, we could collide protons in the same tunnel that we first of all collide electrons and positrons.
Like protons and antiprotons.
Oh, no.
No, protons is...
Protons and protons.
Yeah, okay.
So that's one possibility that's being pursued at CERN. And I think that at the moment, that's actually CERN's preferred option.
Okay.
We could also collide electrons and positrons, but instead of having them going around in circles, you fire them at each other along a straight line.
Like a linear accelerator.
Right, so it's a little bit like firing two rifles at each other and hoping that the two bullets will hit each other. So this is something which has never really been done, and I still have a little bit of concern about whether it would really work as well as the advocates think. I mean, this big circular ring, you give us the money, we can start building it tomorrow, no problem. All the technology is in hand. But I think this is not necessarily the case for the other ideas.
But is it on the track for example, Stanford Linear Accelerator? The technology is similar or different? Or
Right, well, so at Stanford they have this linear accelerator, which is now used for other things, but back in the day it was used for particle physics. And at one point they built a collider which involved taking the beam produced by this linear accelerator and then splitting it into two bits and sending them around curves so that they would collide with each other. So it was called the Stanford Linear Collider. In fact, it was not a linear collider, it was a non-linear collider because I had to bend the beams around and bring them back together again.
Stanford linearly accelerated non-linear collider.
Exactly. So I think it was a very ingenious object, but it's not really competitive with LEP. It just couldn't get as many collisions as because if you're in a circular ring, then the particles can go around for long periods of time, and they've got many chances of hitting each other. But if you're firing two rifles at each other, then the bullets only have one chance to hit.
Yes.
Right. Anyways, but CERN has also been studying the possibility of a very high energy linear electron-positron collider, the CLIC project that you mentioned. But right now I'd say that's not the primary plan at CERN. The primary direction is this circular collider. And then the people, particularly in the US, who are thinking of trying to collide muons. So that's kind of a challenge because, first of all, you have to make lots of muons. It's much easier to make lots of electrons because ordinary matter contains large numbers of electrons already. All you have to do is just extract them from the atoms.
The muons are much heavier leptons.
Yeah, so the muon weighs 200 times as much as an electron, and so it's complicated to produce them. And then you have to sort of squeeze them down so that then when two clouds of muons and antimuons collide, there's a significant chance that one of the muons will hit one of the antimuons.
And not to go one pass through other.
Right. And so although in principle people know how one could do that, it's never actually been demonstrated. And so I think there's a long development path which would need to be followed to build such a device. So the Americans are thinking about that at the moment. There's a lot of interest maybe in setting up a development scheme for that muon collider.
And for the muon collider, is it much better to have linear collision, linear acceleration and collision, or circular?
It would be circular. Right. So anyway, those are the three principal ideas that are being discussed. So as I said, at CERN, we're thinking about a large circular E plus E minus collider followed by a proton-proton. And in China, they're thinking of a similar project, whereas in the US, they're thinking more about a muon collider.
Okay, so stronger colliders, stronger accelerators, and if we look within the standard model of elementary particles, what should we expect to find when we collide electrons and positrons or muons?
So the first step would be to make very high precision measurements with these electron-positron collisions. It would produce orders of magnitude more collisions than what were observed with the Large Electron-Positron Collider in the 1990s.
Mm-hmm.
And the idea is that by making detailed studies of the Z boson, the boson responsible for weak interactions, and the Higgs boson, then we could maybe get some indirect indication of possible new physics.
Mm-hmm.
But to actually find direct evidence, probably we would need this high-energy proton-proton collider, which would be a second stage of the large circular tunnel project that I mentioned.
Mm-hmm.
But the idea would be to go to energies which are at least 10, maybe 15 times higher than what we have with a Large Hadron Collider. And so I think that's a great long-term objective, but it is kind of a long-term objective.
Mm-hmm, mm-hmm. And the money which we need to build that, is it 10 or more times larger than for the building of LHC or something similar, or much more?
So the electron-positron collider, that would cost something similar to the LHC, not a much larger amount of money. The proton-proton collider surely would cost more money. But the hope would be that by the time people are ready to build such a collider, by the time the technology is developed, maybe 20, 30 years from now, maybe they'll have more money.
Or the technology will advance so much that some things which are now too expensive 20, 30 years from now, which will be much more affordable. Yeah.
Right.
Yeah. Okay, so a great amount of what we were talking about now is the advancement of experimental particle physics, and a lot of things are happening in the experimental field of particle physics. But what about the theoretical physics? And when we look at the let's say input of new students and so on, I suppose a lot of them are going into the field of experimental physics, particle physics, but the theoretical particle physics part is something which also is interesting for me, at least. But I got sense that there is a much more things and problems to deal in the experimental particle physics part of these all kind of things than in theoretical. What is your?
Well, of course, there's many more experimental physicists than there are theoretical physicists.
Yeah.
But you need both. Right? They work hand in hand, and science advances through some sort of dialectic between the theorists and the experimentalists.
Like an Ouroboros.
Right. So maybe an experiment finds something anomalous, and then they ask the theorists. Or maybe a theorist comes up with some new theory and says to experiments, well, why don't you look for that? So it goes around in circles. If I look, back over my own career, I've seen this sort of circular process taking place. Just to give you an example, back in 1974, an experiment discovered a new particle, which was completely unexpected. So they went to the theorists and said, well, what do you think this is? And the theorist said, it must be a bound state of charmed quarks. and we hadn't thought it would look like that, but actually, now that you tell us, yes, we can understand why it looks like that.
Mm-hmm. That's Lee and Goldberg, or detection of charm quark, or not Goldberg.
No, it was discovered simultaneously by two experimental groups in the US, one led by Sam Ting and one led by Bert Wichter.
Mm-hmm.
So Sam Ting was working at Brookhaven Laboratory on Long Island, and Wichter and his team were working at Stanford. So I think that's a very interesting example of how an experiment discovered something unexpected, which then when they discussed with the theorist said, oh yeah, well, we should have expected that.
Mm-hmm.
So subsequently, with the development of the standard model, I think it's fair to say that theory has been leading experiment in the sense that theory says, oh, well, you should look for massive force-carrying particles responsible for the weak interactions. You should look for the Higgs boson, although we sort of hope it doesn't look like the standard model, but nevertheless you should look for it. So now maybe we're moving into a different phase where the experiments are looking for anomalies, something which doesn't quite fit with the theory. And in fact, this week at this conference in Belgrade, we've been hearing about various discrepancies between experimental measurements and the standard model. I don't think any of them, at the moment at least, are significant. So I'm not planning to lose any sleep over them at the moment. But we should keep an eye on things. On the other hand, I would say that if we come back to astrophysics and cosmology, then experiment has been leading theory for decades. The idea that there should be dark matter was first proposed by Fritz Zwicky in the 1930s. Very strong evidence produced in the 1970s by Vera Rubin. Overwhelming evidence now, but we haven't got the foggiest idea what it is. I discussed some of the ideas, very massive particles that we might be able to make at the LHC, or waves of very light particles, and then there's all sorts of other options in between.
Yeah.
So I think that
very dark objects which are not visible.
So, I mean, that's an area which is experimental phenomena that need to be understood. The theorists have lots of ideas, but somehow we haven't succeeded in closing the loop.
And if we go into the, let's say, deeper structure of the standard model and generally particle physics as a field, as a theory, we are always going back to the, ancient Greek concept of atomism or reductionism. So with much higher energies, we will get things separated in a few smaller. So we are trying to figure out the elementary constituents of the nature of. So things are made of smaller things in that way, and that's the part of the small. But what happens when you come to such enormous energies that you have Planckian scale particles or whatever we call that on one hand, but on the other hand we have in a sense of unification, grand unification of theories. We have gravity, we have gravitational field force, which is completely opposite in a sense. So when you collide two massive bodies, two black holes or something like that, you just get a bigger object, more massive object. That's in a sense an opposite of reductionism and atomism.
Yeah, well, there's some very interesting speculative ideas that there may be some deep connection between the very small scales and the very large scales. And well, one of the reasons why people are thinking about this is we talked about dark matter. We didn't talk about dark energy. Mm-hmm. So dark energy is a density of energy which seems to be spread throughout all of empty space. Mm-hmm. So you take out all the particles. You'd say, well, there's nothing left. Wrong. There is. Yeah. There is some density of energy. And this seems to be causing the expansion of the universe to accelerate at the present time. Now, the amount of that dark energy is incredibly small on a particle physics scale. So, for example, if in the standard model you asked me to estimate the dark energy, I would have said, well, maybe 10 to the 60 times larger than what's actually been observed. Mm-hmm. And if you asked a quantum gravity person, they might say, well, 10 to the power 120 times as much as what's been seen. So it's a real puzzle, not that there is dark energy. It's a real puzzle that the amount of dark energy is so small. Mm-hmm. And so that's really suggesting that in our chase towards ever higher energies, somehow there's something that we missed at very low energies, or some sort of connection between the very high energies and the very low energies that we haven't understood. So that's a very interesting thought, but I'm not sure how to turn that into an experimental program to actually investigate. Mm-hmm. But I think that one very interesting frontier that's now opening up is new experimental studies of gravity, Einstein's theory of relativity, which we didn't have previously. So I mentioned earlier on my personal interest in gravitational waves, and you mentioned black holes merging to make bigger black holes. So what's been observed so far are the mergers of black holes weighing maybe a few dozen times the mass of the Sun. Mm-hmm. But we know that in the centers of galaxies there are black holes that weigh millions or billions of times the mass of the Sun. So how do you get from these small black holes to those big black holes? Mm-hmm. And so I think that's a very interesting astrophysical question, which I'm interested in exploring, in particular with our atom interferometers. But the hope is that, with all these experiments ongoing and planned to study gravitational waves, that we'll figure out some way of detecting quantum gravitational effects.
Okay.
So far, I don't think people have come up with any particularly convincing idea, but it's early days yet. Let's keep on studying gravitational waves experimentally. Let's keep on thinking theoretically what you might be able to do.
Uh-huh. So when you say people are still looking for an idea, you are talking about the idea for experimental design, or for idea for quantum effects, which people should look for?
So the question is there some experimental manifestation of quantum effects that one could actually observe? And well, there is one which has been proposed, which is that if you go back to the very early history of the universe, it seems that it expanded exponentially rapidly through something a little bit like today's dark energy, but on a much, much, much higher energy scale. And because it occurred at a much higher energy scale, maybe that would give us a direct window on a theory of quantum gravity. Mm-hmm. And specifically, what probably happened is that there were quantum fluctuations very early in the history of the universe which distorted space-time. And the race is on to discover the quantum manifestations of distortions of space-time. Mm-hmm. Now, that's not really sort of getting deep into the mysteries of quantum gravity, but it would be a first window onto quantum gravitational effects.
Yeah, so it will be some kind of observational evidence of quantum gravitational effects.
Right.
And people are looking that into microwave background radiation, or?
Yeah, so this is more precise experiments looking at the microwave background radiation, in particular looking at polarization effects. And that microwave background polarization, of course there's other mechanisms whereby it might be generated, but one of the mechanisms is quantum gravitational effects in the very early universe. So
you're talking about the bicep experiment or something advanced?
Right. So you mentioned the bicep experiment, which
bicep too,
a few years ago claimed to have observed this polarization effect, but turned out that they had misinterpreted their data.
They detected dust.
But now there's more advanced experiments, and they're pushing further and further and trying to observe this polarization effect. And there's two big future projects which are being prepared. One in the United States, which is a sort of ground-based project, and then there is a space experiment called Lightbird, which is being led by the Japanese, but with participation by other countries. And so maybe by the end of this decade, we'll finally see this polarization of the microwave background. So.
And when you look back through your career from, let's say, when you were a bachelor student and working with all kind of different problems at different institutions, from Caltech to LHC and so on and so on, how do you see this, should I say crisis of particle physics today, or should I say, I don't know, all kind of different interesting openings? How do you see that in a context of all kind of historical situations which happened similarly or less similarly? What you can tell people who are listening this are maybe I don't know, eager to figure out that direction in which particle physics should go as fast as it is possible.
Well, I personally feel this is a very exciting period because we've got this paradigm, the standard model. This paradigm has now been established, but it's an incomplete paradigm, and we need a more powerful paradigm, whether it's unification of the fundamental forces or quantum gravity or dark matter or dark energy. There's all these issues that the standard model does not address. And so we're in a situation where we have a very solid basis for the next round of theoretical and experimental advance, but we don't know what direction. We don't know whether we have to push in this direction or that direction, and we don't know whether we'll be struck by some phenomenon coming from over here or coming from over there. So I think it's a very exciting period. And I personally feel as excited now in the 2020s as I did in the 1970s, when we moved from a situation where we really didn't know what we were doing to the discovery of charm particles, which we discussed briefly, which then led us on towards the standard model. So here we are, we're looking around, we're trying to figure out different experiments that we could do, trying out different theories. But, tomorrow maybe somebody's going to come in with some experimental breakthrough which is going to point to us which direction to go. So my personal plan is to be ready for whatever happens. And I try to tell my younger colleagues, of course, you have to pursue your research line and develop some expertise, but keep on looking around, reading other papers that maybe don't seem to be directly related to what you're doing, but to build up this sort of background knowledge so that if all of a sudden there's some new astrophysical phenomenon which tells us something about fundamental physics, then you'll be ready.
Yeah. And what do you think about the vast number of papers and vast number of knowledge and theoretical and experimental ideas which are present now, maybe more than ever, in one particular field, particle physics or small field? And what do you think about that? Is that leads to I don't know, the growth of knowledge, or it is just problematic to see through all those papers, and should there be let's say one Renaissance person who can encompass all of that and figure out what is the direction, or we are way beyond that and we cannot do that anymore?
So I think that it's very difficult for any one individual to really follow what's going on in the whole area of particle physics.
And astroparticle physics and string theory and so on.
Cosmology and so on and so forth, And if you do try to follow what's happening in all these different areas, then your knowledge will necessarily be superficial. There's just not enough hours in the day to read all the papers that appear every day. So you have to, what I do is I look every day at all the papers that are released electronically on the preprint archive. I look at what's happening in experimental particle physics, theoretical particle physics, some of the astrophysics, and general relativity. So I'm just sort of on lookout for things that catch my attention. I don't read all those papers. I couldn't possibly read all those papers. And so on an average day, maybe there's a handful of papers that I think look sufficiently interesting that I look a bit more carefully at the paper. Maybe I download it to my computer. Maybe I print it out if it's particularly interesting. But indeed, it's a challenge to try to follow what's going on in all the different areas. And so I think it's absolutely essential to talk with your colleagues. I think conferences like this one here in Belgrade play an essential role because you can get exposed during the talks, of course, but also just in the corridors, chatting to people. What did you think about that talk? Oh, it's just bullshit because it's garbage, whatever. That sort of informal interaction is invaluable. And of course, for 2 or 3 years, we didn't get that because of the COVID pandemic. And for many people here, this is the first big conference they've been to in several years. And a lot of people commented to me, how refreshing it is to hear all these ideas and just renew the contacts with their colleagues. Yeah,
to drink coffee and informally chit-chat about things. Yeah. Okay, thank you very much. It was really nice to talk with you. It was a really rare opportunity to have a guest like you here in Belgrade and in my show and so on and so on. So thank you very much for that.
Well, thank you for the invitation. It's always interesting to discuss with interested non-experts. Often you sort of look at what you're doing in a somewhat different way, and I think that's also very useful for us.
And you're a really big advocate for science and physics and particle physics. You talk a lot on kind of different opportunities, and also big advocate for CERN and along all kind of different countries. You're trying to bring people together to work on that. It's really
well, I'm a firm believer in science for peace, and as I mentioned in my public lecture yesterday, I think I regret very much that countries that were previously collaborating in a friendly way are fighting each other. And I think that's harming science, and that will harm science more if it continues. I hope very much that the situation calms down and we'll be able to resume scientific collaboration and scientific discovery on the scale that we were doing before.
Yeah, I hope that too. Thank you.
Okay, hvala lepo.